Welcome to the next webinar within the series of Eurosite remote sensing webinars. I'm Wojtek Mróz, and I will host this webinar on behalf of Eurosite, the European Land Conservation Network. It is our second meeting in 2021. 2 weeks ago, Richard Lucas from Wales was speaking about using Earth observations to inform on changes within protected sites. And today, we invited Jose Manuel Álvarez-Martínez from the University of Cantabria. And the title of the webinar is Habitat Mapping Using Different Remote Sensing Platforms. Okay, I'd like to tell you that I'm a botanist and ecologist, and for many years of my field research, I've been just dreaming about such remote sensing methods that are so easily available today. And now I feel that having all of this at our disposal, we are not making full use of this potential. The idea behind this series is to fill this gap. We want to improve cooperation between remote sensing experts, practitioners, and site managers. We want to show that remote sensing methods can be inexpensive, relatively easy to use, and above all, allow us to obtain accurate, current data of great importance for biodiversity conservation. I'm sure that a lot of you know quite a lot about our Eurosite network, but before I invite my colleagues here, I would like to say a few words about our network for those that are here for the first time. So, I will represent Eurosite, the European Land Conservation Network. What was the main idea to create this network more than 30 years ago? It was to provide opportunities for practitioners to network and exchange experience on practical site management. So I would say that even in the one sentence, it's all what should be said about this network. So we are trying to be kind of bridge between practitioners, site managers, and researchers to find a better way to make our Europe such a place where nature is cared for, protected, restored, and valued by all. And within our network, there are several working groups, and we like to think about these working groups as a kind of bottom-up initiatives created by our members. And this is a real place that this cooperation, this flow of information between all stakeholders and other interested people is done. So first, our first working group is Economics and Ecosystem Services working group. The next one, Wetlands and Climate Change. Eurosite Management Planning Expert Group, Remote Sensing Support Group, and this is the group that is organizing our today's meeting. Peatland Restoration and Management Group, and Agriculture and Biodiversity Conservation, the newest one. Our network consists of 72 members at the moment, with 41 organizations, both public, private, NGOs, and 31 individual members. From 24 countries across Europe. These are governmental and non-governmental organizations, individuals, as I said. And we are focusing on Natura 2000 sites, but not only, I would say, that any other natural areas in Europe. And our secretariat is created by 5 staff members based in the Netherlands, in Tilburg. So also, if you would be interested in becoming our member, please visit our website or write us at info@eurosite.org. Now I would like to invite here our chairman of the Remote Sensing Support Group, my great colleague and excellent ecologist, Clive Harford, speaking straight from Wales.
Hello, thank you, Wojtek. Okay, I'd just like to say a few words about the group and what we are, the remote sensing group that is, and what we would like to achieve and what we are setting out to achieve. The reason that the group was formed initially is to form a bridge between the remote sensing sort of technologists and sort of nature conservation practitioners, because we were aware of the gulf that existed between the people who were developing these things and the people who were trying to implement and use remote sensing on the ground. The way we envisage being able to do this in the long term is through a series of hubs scattered throughout Europe, so in as many European countries as possible, so that the meetings can take place in the first language of the country and not in English, as we have to with these sort of multinational events. But and we call these things sort of information exchange hubs, where we have remote sensing technicians and nature conservation practitioners together, where there can be an interaction so that the remote sensing people can get to grips with the type of issues that the ecologists and the nature conservationists need to get to grips with, and then, you know, equally, then the remote sensing technicians can feed the information back on how they think the best way to deal with those things are. So that is the plan. And if it hadn't been for COVID, we would have hoped to have actually started some of these things last year. And we are still hoping that possibly later in the summer, if things go well and the vaccines get rolled out properly, and that it will be possible to hold some of these events, if again, maybe on a national level rather than international level. So hopefully the people will be able to move within their own countries, even if they can't move between countries later in the summer. But we will see how that develops. So that is the goal, at least. If we can't do it this year, then obviously we will keep pushing forward in the hope that we can do this in the future. So now I'm just, might as well hand over to Jose Manuel Álvarez-Martínez, who is our speaker today. And I'll just say a few words about him before he starts. He's a senior researcher in the field of landscape ecology at Environmental Hydraulics Institute at the University of Cantabria. His main research topics relate to the use of to land use and cover change on vegetation dynamics and functioning. He's particularly interested in large-scale species community distribution monitoring using remote sensing and spatial ecology tools. His main experience is on the evaluation of the ecological consequences of global change on ecosystem functioning and services. And he's also worked with several sort of well-known and international research centres, such as the University of Wageningen in the Netherlands, and the Autonomous University of Barcelona, and Doñana Biological Station, of course, in southwest Spain. So there's a lot of background there and a lot of experience, and I think I might as well just hand over to Jose Manuel and let him take over. Okay, thank you.
Thank you very much, Cliff. Thank you for Bote and Eurosite platform for first creating this research group, this remote sensing group, and inviting people, and in this case, me, to tell all of you, thank you for being there. For talking about something I'm going to share the screen to start talking about. Well, so I hope that everybody is watching my screen perfectly. Well, so as Bote told, the title of the presentation is Habitat Mapping Using Different Remote Sensing Platforms. And that's not specifically, that's not true alone, because what I want to tell you is mainly about how we can merge in situ information to large scale mapping, monitoring, and management using that remote sensing platforms that are different because we need different information for different purposes. So it's not true that with remote sensing and just one image, or only with remote sensing, we can do everything. So remote sensing is something that is there, and we can use it, we have to use it, but we have to be clever. We have to applicate SWOT analysis each time we have to face a problem, for understanding what are we looking for and which information do we have at hand for solving that environmental, that questions, that issues. So in particular, the remote sensing different platforms are a tool, are the pathway for linking in situ information to large scale management at the end. But first, we will go through mapping and monitoring and understanding what do we have out there. Because what we have there is not simple, is not static, because the landscapes that we have, this is the first slide I created in my PhD almost 10 years ago. And I like it because the landscape are dynamics, landscape change, and they come from past landscapes that are modified because of human and natural pressures and change the structure, create different pathways of dynamics, and finally they change the function and ecosystem service that we can get from that living environment. So at the end of the day, we can simplify everything just talking about that we need spatial data. So we need patches. We need that complex landscapes that we have there. We need to create something more, something simplified, something more simple to be able working with the ecological theory. So if we understand the landscapes, like landscape ecological theory tells us, we have to understand that are complex mosaics that are shaped, that are driven by nature and society, that implies a dynamic in the structure and, of course, a dynamic on the functioning. So we have to understand all that complex pool of information all together for taking simplified decision that allow us understand first what is going on, and then to translate in an effective manner to the practitioners, to the managers, or taking decisions based in knowledge, taking decisions based in science. So all that changes that occur, now I am moving to my domains. We are in the north of Spain in an Atlantic sub-Mediterranean area on which we have a very dynamic movement of landscapes because of human pressures that imply a land degradation and a vegetation recovery because of land abandonment mainly. So we have in this area this specific contrast. As I told in the beginning, we have to go to each particular case and understand which are the drivers, meet the stakeholders, understand the experts on the territory, and first assess perfectly what is occurring there. So in our particular areas, we have these main drivers that imply a continuous dynamics of that heterogeneous landscapes that move the pasture land and the shrubland into forest land. If no disturbances occur there, we will have mature forest ecosystems with a quite different functioning to the young forest, but ecosystems that can become again pasture or even bare soil if we use fire in that area for creating pasture for grazing, or just use fire as occurs in my area in the north and mainly northwest of Spain because of a tradition of management with no currently purposes, because we are mainly now suffering a process of land abandonment, except in some areas. So this is complex, as far as you know. Landscapes are complex and landscapes move. They are highly dynamic. So we need tools for understanding that complexity. So the first thing when we start working in a territory is just go into the web and download information. And that's amazing, of course, and amazing when somebody as Richard Lucas showed us something as good as the Living Atlas platform that we heard the last Eurosite meeting. I enjoyed quite a lot. So there is a lot of information over there that can be used. And Copernicus in Europe is like the major point, the major source of information that we can use. Specifically, the Copernicus Land Monitoring Service, the LCLMS, with the different services, global, pan-European, local, and so on, provide us a big amount of information about, I mean, you can explore the website. Most of you know the website of Copernicus Land Monitoring Service. If not, I encouragely recommend that go there and check all information that you have about the riparian areas, the urban atlas, Nature 2000 areas, everything with their uncertainties, of course. They are modeling products that come from space to our screens. We have the highly valuable high-resolution layers with different covering different topics. We have the Greenland cover, the last one from 2018. We have specific national products, as in Spain we have CIOSES, like an evolution of Corinne with a, let's say, similar legend, but with more information and so on. And we have, of course, the CLC Plus objective that is moving quickly towards the backbone and all the products that it will have. We can move a little bit more far away, creating our own products. If we cannot find the information that we need over there, just in the web pages, the not only Copernicus, but also using NASA, Landsat products and MODIS and whatever specific projects, we can create our own products. We can use satellite information, mainly medium resolution satellite information, as Landsat Sentinel, one of the two of the most well-known platforms and sensors with different sensors. I mean, that we can move in time, creating maps from the past, using reference data from the past. For example, this is a slide of my PhD, on which I spent like half a year making orthorectification of all aerial imagery, or having like, let's say, orthophotos, but for the middle 80s. With that orthophotos, I created ground information, in situ information. I applied supervised specification. I made a lot of things for having this kind of maps that change in time land cover. So we can create our own products. Sometimes this is also a slide of my PhD. Sometimes it's not enough with the spatial, temporal resolution of satellite, medium resolution satellite imagery. And we have to go a little bit more in detail, creating land cover maps. We move still in the domain of land cover, creating land cover maps with more detail. So in my PhD, I selected basins in a well-designed sampling strategy. I selected basins and I made a really high detail land cover maps and a scale of 1,000 around, with a legend talking about land cover, mature forest, young forest, and I assessed the evolution in time. Here you have maps from middle 50s to the more or less around the current situation. I went to the field in the current situation. I used the ortho-rectified aerial photographs in the pads. So I created maps for analyzing how land cover and land use, and climate interact and modify landscape structure in the future, and how that landscape structure affects the functioning. In the particular case of my PhD, and in the particular case of the work I'm doing, the most of the work I'm doing here in the UH Cantabria, is how land cover dynamics and so on, this landscape structure affect water quality, affect the hydrology of the rivers that are in that basins that we are analyzing. So that's good. If that covers my objectives, that's good. I didn't explain it in the beginning, but what I'm going to say is just go in a very simple way, in detail, in a GIS format, on how solving this kind of problems of producing spatial data. Of course, we can download the data. We have operational procedures. Once we have the theory clear, we know the data, we know the result that we are looking for. We can include everything in more operational procedures using the IT technology that we have today, all the IT capabilities. But I will go through the presentation towards a more GIS desktop, format, to allow you to understand how we solve these problems. Once solved, we move into more operational systems, okay? But as I was saying, with these kind of maps that we download or we create with the satellite imagery, with the aerial photographs, we create spatial data that in this particular case, solved the objective that was assessing, understanding how water quality and hydrology changes in the basins. But when we want to talk about vegetation, when we want to talk about habitats, is one of the keywords of the title, yes, habitat mapping, we have to talk about vegetation. So we have to disentangle a little bit more that spatial patterns across the environmental gradients that we have in our study areas. It's not enough saying I have here forest. And it's not enough saying I had not this forest 20 years ago. But we have to move from the top of the mountains to the coastlines across the vegetation, across the topographical gradients. And it's not enough downloading some beautiful maps that are on the website, because that patches that look like homogeneous patches in terms of forest are not homogeneous when we are talking about vegetation. We have different species, not only different species, we have different communities, we have different species, and we have different ecological statuses in the base of different indicators of structure, function, and vulnerability. So we change the composition, we change the function, we change the structure, we change the pressures that we have across space. So it's not enough having this kind of vectorial format vegetation maps based on patches, because that patches are not homogeneous anymore. So we need information. We need in situ data. This is the second keyword I wanted to highlight in the title. So moving in situ data towards landscape management. We have a big pathway in the middle that I will try explaining during this time we'll be together. And the first thing we need is just the in situ information. And that in situ information needs to be collected following expert criteria. And the picture appears, my colleague Borja Jimenez Alfaro is maybe one of the most deep collaborators. As a botanist that has a big knowledge on the landscape, on the vegetation patterns, and we combine that expert knowledge on vegetation with the expert knowledge on remote sensing and spatial modeling to arrive finally, you will see, in this landscape management. So the good part of the picture is that in situ data, I will repeat this during my presentation quite a lot of times. In situ data, it's a complement. It's a complementation of remote sensing, or better, remote sensing complements the in situ data capabilities. It's a cost-effective solution that allows us enlarging that observations from local points on which we observe, because we cannot never observe the whole territory. It's impossible. It's absolutely impossible, even in developed countries. Of course, in countries that has not a lot of money to invest in this, let's say, environmental protection or whatever, there is no time, there is no people, there is no money for observing the whole territory. So remote sensing is a tool through modeling that allows us enlarge that observations, okay? And as far as you know, it occurs because the remote sensing capabilities allow us discriminate, differentiate the different land cover types, and not only the land covers, but also the different vegetation types, different indicators about the conservation status of vegetation at the level of structure, at the level of composition, of course, that species and communities, and to have different responses in what we call the resolutions of the image: spatial resolution, temporal resolution, vector resolution, and so on. So this was the issue that we faced, in particular when I arrived here to the Institute, to Cantabria, because there was a need for creating the technical basis for the regional management plan of Nature 2000 areas. So the regional government needed to understand what was going on in the whole territory of the region in terms of the spatial distribution, conservation status, and some guidelines for the management plan of the different habitat types that they had in the region. And there was not information for the whole territory. There was just some specific location. There were some specific locations with information that were created with field observation, photo interpretation, that they needed everything that the Article 17 tells us that we have to fulfill for reporting Nature. So they needed the spatial data that went much more far away of land cover and much more far away than something that was observed in situ. Some couple of years later, we have a very good collaboration with the Basque Country government, because they had information from Nature 2000 covering the whole territory, very high quality information, following a UNIS classification type of the habitats, with information about conservation statuses and so on. And they wanted to know how this kind of methods, hopefully in situ previous information plus remote sensing, were able to repeat that results. They wanted to know the capabilities of this approach, and we made a very good collaboration with them, showing that around, let's say, 70% of the territory can be covered with these kind of techniques, while other places, of course, or the habitats or the places needed to be addressed in more detail than this kind of modeling using medium resolution satellite imagery. We only work with Sentinel and with Landsat for time series, but we have more tools that we will see later. And the big brother of all this, we made a project. I was working with Borja, with Santiago Garcia, and many other people in Turkey during a couple of years, for creating habitat maps for the whole Central Anatolia region, for afterwards making a selection of the Nature 2000 areas in the base of all the requirements of the Habitats Directive, Habitats and Birth Directive, put on the table for defining the areas to be protected. It was a very beautiful exercise, quite demanding on time and effort, but we followed the same procedure that was this. This is the general methodology. So we first need spatial data. We need spatial data about vegetation. So we need habitat mapping. We need covering the patterns of vegetation. We need understanding that patterns at different levels that we will discuss later on. Afterwards, this is the big chapter of the presentation. Maybe we can focus only the presentation in this chapter, habitat mapping. But habitat mapping is the first step since my point of view, it's a way of teaching this. It's the first step of 3. Second step is once understood the patterns, we need to understand the processes and dynamics. That's what we have been talking in the beginning. Landscapes are not static, so we cannot understand the patterns and that's all. We need to move much more far away on the pattern. We need to go from patterns to process and dynamics. For what? For understanding what will happen in the future and the different scenarios. For understanding what do we have now coming from the past. Which are the results of the past policies applied? What do we have now? We need to understand the ecosystem services now and in the future, what will happen in the future. So for allowing us applying a very good and objective monitoring and finally taking suitable management decisions. These 3 main steps can be disentangled in more short steps that we can go much deeper and deeper. But basically, all of them imply creating models. From the models, we get maps. With the maps and information and ancillary information, we create indicators for the patterns. With that indicators, we can understand if the habitat types, if the territory is well preserved or not, or applying finally conservation or restoration actions. So let's focus on the habitat mapping. This is not new, of course. We have been since the last century applying a monitoring of vegetation. The novel thing is one thing that we have not done. So we have not in the same, let's say in the same product, in the same map, and in the same pool of information at a fine resolution with accuracy or a reliability high enough for talking about fine resolution, but covering large scales. So the in situ information can be very accurate, but is located in a specific point or points or parcels or study sites. And when we are talking about geographical coverage, information about vegetation in the whole world, we move towards something that is more rough. It has not a fine resolution because it's not possible. So that we want to fill that gap with the habitat mapping using remote sensing. We want to cover large territories, but at a fine resolution. And always fulfilling the requirements of the official end user, so the official end managers. Here, the Ministry in Spain, as we will explain to you later on a little bit, publish guidelines on how making a monitoring of habitat types, of ecosystems, better said, and we are trying fulfilling all the requirements, but using this approach based on remote sensing. So more or less we know what we have to do, but we have to start thinking about. We have to breath and apply a SWOT analysis, saying, okay, what is important here? So what actually matters when mapping habitat types with remote sensing? I like this simple slide that I always use. I don't know if somebody has seen my presentations, but it's quite similar. Most of them in some parts, because it's necessarily being similar, because this is the important thing. So what actually matters for mapping habitats, for mapping vegetation? First, a classification system. We need to know what do we have to classify. In the same way that when we work in landscape, we say, I want to map forest. Everybody understands more or less with differences, personal differences, territorial differences, what's a forest. A forest is not the same officially in Spain than in France because of the size of the grain size, because of the coverage of the crown canopy and so on. But everybody understands what's a forest. So we need a classification typology saying which kind of vegetation types do we have to map. Then we need occurrence information talking about the distribution of that typology. So this is the in situ data, the ground data that can be obtained from field, from previous maps. It's different, the methods that we have to apply afterwards, depending on what are we using, but we need occurrence information. It's the in situ data about that typologies. Then we need the predictor layers. We need to extrapolate that observations and using, of course, a modeling procedure. It's a modeling technique, an algorithm that can move from typical ordinal least square regression until artificial intelligence with convolutional neural networks that we are using today with deep learning and so on. So we have a modeling procedure, okay? So let's go step by step, showing some tips and or discussing afterwards a little bit about these 4 boxes important for habitat mapping. When you see something cool as the website that Richard Lucas showed us last week, you can see, okay, this is quite easy. I go to this place and click. But behind that, I cannot imagine the amount of work that guys have done for getting that beautiful maps at the end. So, I can imagine because I am going to show you. These are the steps. They first need a classification typology. We are using in our work, the most of the people in Europe, and it's the official classification typology of Spain for monitoring habitats is UNIS classification typology. But when we're talking about UNIS, we have different levels. So we have to take care of putting everything in an homogeneous language. I mean, having more or less the same level of UNIS, talking about the habitats with the same level of depth, for not talking about UNIS level 1 or 2 when we're talking about woodland, and UNIS level 4 when we're talking about wetlands. So we have to homogenize more or less information. So that's what we did here in the north of Spain, on which we are working out towards the whole north, mainly the northwest of Spain, with collaboration of Borja, Jimenez Alfaro, and other botanists. So we defined, a level 3-4 of UNIS. It's a level 3 of UNIS, but because of the regionalization, sometimes it's a level 4, for having a list and afterwards go into the field to collect occurrence data. So this is a brainstorming. I mean, we have to cover the whole span of information. And somebody can think, okay, I have core inland cover, or I have vegetation maps that I can get from the different web servers. So I download that information and that's all. Maybe you can think that. But what happens? What happens is that points refer to that problem that I showed you before, that the land cover patches are not homogeneous. Imagine that the green color that I have here in the presentation, imagine that the green color is forest, and you put a point in the middle of that patch. Behind that patch, maybe you have not a forest, because that forest patch has a 60, 70, or 80% of coverage of forest. The other parts are shrublands, even urban. If you select only the patches with 100% of coverage of, let's say, a particular type of forest, the issue is that you will have less than 5% of the territory with information. So there are trade-offs there between the quick I can get information and the efficient that information is. This is the issue that I told you before. So the patch that was forest before in this picture is not everything forest. So the red line, the red arrow showed us a shrubland, maybe some fringe community, but it is not a mature forest. So I can, this is the region on which we focus mainly our work, even though now I told you that we are moving to the whole north for our analysis. But I can cover the whole territory of information with previous maps about core inland cover, the forestry map of Spain, and so on. But that maps are not talking about vegetation, or just are talking about vegetation with quality enough in just specific locations. So I can use better maps. I can move toward the Basque Country. I told you that we had there a very good maps about UNIS, or we know UNIS typology. Or I can use that maps I created that are highly accurate. I know that patches are mainly oak and beech forest, and I have also an identification of specific patches of vegetation types. The issue is that these patches are neither homogeneous 100% of times, and I have not a detailed specification of the plant communities for getting information enough about the habitat type and the conservation status. And I need expert knowledge. I am not a botanist. I would like, but I am not. I'm a landscape ecologist. I have knowledge about botany, but I'm not enough. So we need expert knowledge. We need in situ data that can only be provided by specific field campaigns. Field campaigns, or at least expert people managing that maps, or field campaigns collecting the information that we need and taking into account issues that we never take into account. We need to cover the whole territory with information. We need to cover the whole environmental gradients with information. For example, imagine that we are sampling oak forest, a particular species, a whole oak forest, for example, and we only locate the areas of holm oak in, let's say, shady slopes and lower areas and closer to paved roads. So we are creating a bias in our sampling. So that's not good. We have to cover the whole territory, covering the whole environmental gradients, and also take into account the autocorrelation issues. In the base of the information that we are going to use for modeling, we cannot just put 1 point and 20 meters far away another one and 20 meters far away another one, because we need to take into account a lot of statistical issues that will make our predictions reliable. Okay, that's not the topic of this speech, but it's a very hot topic that you have to take into account when you use this. Another issue is how collecting the information. Typically, this information is just written down in notebooks, and we arrive to our places, and we change the point from the GPS. Maybe the GPS, we have a datum, different datum, that the WGS is the original one of the GPS. So we are accumulating errors. And at the end, maybe our GPS point, if we don't check in the orthophoto and we take into account that all that sources of information, that GPS point moves and we are accumulating an error. So in the project of Turkey, because of the field botanists were not very familiar with these GIS-friendly facilities, we created a tablet system we call. It's a tablet on which they just click and insert and put information in a database. So that means that information is accurate when taken on the ground, and we go to the modeling environment with that information with no more errors than the ones that we will have yes or yes. So at the end, we have not a lot of information, maybe covering the whole territory, but it's GPS information with high quality. This slide, is for 1 year and a half ago. Now we have around 5,000 points covering the whole area that are GPS points made by botanists with information not only about the habitat, but the species, the typical species, the conservation status indicators that give us confidence when using that information. Now, as I told you, these numbers are, for example, from different types. Here is following not units, it's following the Annex 1 directive. For different habitat types, European dry headlands and others for shrubland pastures, we have around a couple of hundred of points for training and for testing. I didn't mention, but of course, in situ and ground data is not only for modeling, need to be reserved also for validation. The really interesting thing would be split completely the modeling, the training and the validation, not only in 2 data sets, but also in space and time. It's not fair if we collect a big amount of information and we don't take into account the spatial autocorrelation, that will make a split of 70% of the information for training, 30% of the information for validation, because that's tricky. If we have a spatial autocorrelation within our information, we will increase quite a lot the validation, but that's not true. So this is, you can read quite a lot. In fact, one of the questions I suggested for further discussion talks about that, we have to read quite a lot and to take into account that it's not everything as simple as we think. Okay, we will discuss afterwards. So now we are enlarging these numbers to the whole territory, but that's tricky. You can see in the picture in greener colors, you can see more or less the areas covered by ground information, but this area is quite large. So it's not possible to apply the method that we followed in Cantabria region of covering the whole territory. We have no time, we have no money, we have no people. So the good thing here is to work together, to put all the regional governments to talk among them and say, okay, each one of you, because here in Spain the competence for territory management is from the autonomous regions, to put them in common and say, okay, yes, do your own work. We don't mind, of course, it's your competence. Continue working with your in situ data, continue working with your own procedures of monitoring the territory, the vegetation, Nature 2000 or whatever. But let's put in common all the in situ data that you have. Let's create crosswalks for putting everything in the same language, as I told you, in the units type, at the level 3, for example, if possible, or modify whatever, but having the same language, and then with remote sensing that already covers the whole territory, as I will tell you later on. We can run this kind of analysis at the biogeographical level region. at the geographical region level, sorry. I mean, we can cover all the territory with homogeneous information talking about the distribution, conservation status, and disturbances. And that will be homogeneous. That will be replicable in space and in time, and that can be subject to analysis in the context of climate change or global change or whatever. And we are in that picture now in the north of Spain. That's what we did in Turkey. I move again to that Big Brother project of Turkey. That there we collected more than 200,000 in situ points. We were 2 years, 40 people working during 4 months in the field. They collect with a tablet system. They collected a large amount of ground information that we use for making good models and making exercises of sensitivity and so on. And now we are working on a very good paper that hopefully see the light soon. But this is quite expensive. The project was a Europe-paid project. We have the capabilities, but that's not the typical thing. So I don't want. I think we can continue a little bit more, but I put here some reflections, some questions that we can move afterwards in the discussion round, and that Botte had already for moderating the discussion. That has to do mainly about what do you think about this thing of in situ information, using maps or not? Have you ever done this? How to put in combination with reality? And what about the absences? I mean, we are talking about occurrence of information, but when we model, we need absences. How to manage that? This is a very hot topic in the literature. I spent a postdoc a couple of years just working with this issue, and I actually like, of course. Next step is the predictor layers. And of course, Botte, if you want to stop me, you want to make a break, we can do.
Yes, because we've got 2 questions from our audience. So
we'll stop here for a while. Perfect.
Yeah, just stop your presentation for a while. So this first question asked by Bogdan Trotz from Ukraine, Carpathian Danube Initiative. What is the best approach to start habitats mapping for protected areas where still capacities need to be built for that?
Yeah, so I clearly would say that it's defining these 4 boxes. I mean, if there is no information, if there is no let's say technical and economical capabilities of doing anything, for me the worst thing is just doing whatever. So it's much better to create a roadmap, saying, okay, what are other people doing here? With the people that students of the group and the people that are doing the PhD, the first step is boring, but the first step we always do is reading quite a lot. Just getting information of what to do. So first, once you understand what you have to do, that can be briefly defined as these 4 boxes. You have to start. You can start thinking about what you can do. So maybe it's easy. Classification typology. I will work with units. Occurrence information, which maps do I have? Once you collect all that information, you can do something with that information or not, you will have to see afterwards. You have to check if that information follows the typology that you defined. You have to get information to check with, as I will explain you now, with the predictor layers that we have. For example, imagine here in Spain, we have LiDAR covering the whole country. I can take maps about forest, and I can take points for modeling. But if I cross that points with LiDAR, and LiDAR is telling me that the altitude, the average height of that vegetation in that point is 0, that's not a forest for sure anymore. Or at least there is it's not coetaneous, the information of the map, the LiDAR, and my current situation. So you have to think about what do you have, is making an SWOT analysis. What do you need, what do you have, and how doing your best for start talking. And my next advice is putting an expert to work with you. I always did since the beginning of my PhD. I wanted to do very good work in land use, land cover change analysis, and I start connecting with the people of Wageningen, for me, one of the best ones. And I found there very good people that helped me understanding what I wanted to do.
Okay, I got another question, also asked by Bogdan. What is better, to use UNIs or national habitat types in practice?
Well, it related to the previous question. If you have a lot of information following one typology, your national database, ecosystem, classification, whatever, you can use it. But the good thing is having the crosswalks, having the bridges that links one to the other. Sometimes the bridges are not one-one. You have not an equivalence of one habitat type in one typology, in one classification typology, with one habitat types in other classification typology. But you have to deal with that. You have to sit and think what is better. For me, I would advise to use UNIs because it's like the universal is not perfect. There are a lot of people telling that UNIs is not good, it's not enough. Okay, maybe it's not, but it's something that is defined at the European level, is well structured, is hierarchical, and for me is quite useful. Of course, when we are talking about habitat mapping with these techniques, we accept some kind of generalization. We are not talking about the specific, detailed information for a project, for a restoration activity that you will have to go in detail. But for that kind of medium scale habitat mapping for repeating in time and so on, I would recommend using UNIs. But if your information is in another one, you can create the bridges, the crosswalks.
Thanks a lot, Jose. And another one by Karen Fake. Did you consider collecting polygon data instead of point habitat data?
Of course, if you can, I mean, there are a lot of things that maybe need to be explained more carefully. I am not talking about using only points. No, I am talking about using sampling procedures. So when sampling, you need to define strata. You need to define the gradients that you have in the territory. I will show you a slide afterwards about this. But when you create like strata, you define the gradients of your territory. What you are doing is being sure that you will sample the whole territory and being sure that you will sample the whole gradients. Afterwards, you can just take points or you can take parcels, polygons, but always homogeneous. What you cannot do is to take polygons that are heterogeneous, because afterwards, if you get the signal from the satellites from that polygons and so on, you will get into troubles. Of course, if you use points, sometimes you have to create the region of interest. If some of you are users of remote sensing software, you are talking always about the region of interest or the area of interest. That are polygons. But you can use, for example, seed growing approaches with using the Euclidean distances between layers for avoiding making polygons that are mixed. So I am talking about sampling, not about points or polygons. I mean, what I want is to cover the whole territory with a clever sampling procedure instead of just trying to map with polygons the whole territory.
Thanks a lot, Jose Manuel. And another one by Tom Harrison. Are you able to share any more detail about the Horizon 2020 tablet system used in Turkey? We are trying to introduce the use of tablets for sampling by ecologists in Wales and would be grateful for any advice or lessons learned.
Yeah, well, I have more information about the tablet system because I understood you correctly. It's about the tablet system, no?
I hope so. Tom, if you have any more explanation or clarification, just write your Q&A.
Yeah, well, maybe I missed. Well, yeah, what we found in Turkey was a territory with no information at all. And we found a number of people for working with them. They were botanists. They knew the territory, but we found they were not familiar with the modeling at all. In fact, the modeling was not included in the project since in the beginning. The issue is that they had to cover the whole territory in 1 year and a half. So what we applied was a stratification of the territory. We used in some way, of course, we used Corinne. The last version of Corinne in the area was more or less good for identification of natural and semi-natural landscapes or natural and semi-natural locations. So within that, we started using satellite information, climate information, topographical information, some information that we collected about soil types. So we make strata. We created a combination of all of them for defining the areas that were more or less homogeneous in terms of topography, climate, soil type, and some kind of information about the NDVI, SAVI because of the large amount of bare ground and so on. So once defined the strata, we gave to the stakeholders, to the botanists, the tablets with the database of the habitat types that we have there. We spent 1 year there talking about which habitat types can we find there, creating a list, the official list. Afterwards, they have everything in the tablets. They have the strata, and we divided the territory into 40 different sectors because there were 40 different people, and they went to the field to make transects, to collect information. The first year, we make models, and we went to the field to validate the gaps in the modeling capabilities. So we identified areas that were well modeled, areas that were bad modeled. So we went to collect more information in the areas that were weaker in the quality of the product and the products. And it was very, very good because the people there, they didn't know anything about modeling, but they found that the models were able predicting something that has been not sampled before. And that was a win-win situation, and we engaged it with them quite a lot, more or less. I don't know if it was the question, more or less.
I hope so. So Tom, if you would like to ask something more, just write it again in view Q&A button. So just a reminder for all that all of you can paste your questions via this Q&A window. And as a reminder for Jose that we've got just something like 45 minutes left, even 35.
Yeah.
Okay, go on.
Do we stop, Boste, or I continue? What do you want?
Please continue, and we'll have another Q&A session at the end of the meeting. But please leave 5 or 10 minutes before the end. So you've got 25 minutes now.
Perfect. So, Botte, you can stop me when you want if there is some question, okay? So we are here in family just talking about ecology and vegetation. So you can stop me when you want. So
I will stop you.
Perfect. So it was nice having these questions because they advance a little bit more what I'm going to tell you now. Because now we only have been talking about occurrence data, but we have to go. We have to advance into the predictor information. That is not only useful for enlarging that observation, but also for filtering that information, as one of the colleagues asked. So the information that we have is amazing. It's a huge amount of information that we can collect, and it's over there. One of the main knowledge gaps is knowing where is the information and how to manage the information. So we have information about the environmental limiting factors, about topography, a big amount of digital elevation models, climate databases, and just a few amount of information, large scale, about soil properties that are very, very, very important. In my PhD, I spent 1 year of my PhD. Because of that, I spent the PhD 2 years later of the deadline, creating a soil properties map of my study area because we had no information about that. And of course, we had the remote sensing. We have satellite imagery of medium resolution, Landsat, Sentinel, very high resolution satellites and sensors, hyperspectral information that is there, a LiDAR, radar, and of course, a large amount of level 3 databases with the right information and so on. I will go quickly just because I want to finish with this part before the end. So some information is quite simple. It's just download and process in a GIS environment. So we can download the digital elevation model. This is the digital elevation model that we have for the whole Spain at 5 meters of spatial resolution. Now we have also one of 2 meters, but it's not just to download. You have the tiles, you have to process in GIS and so on. And then you can create slope, annual solar radiation, and others. About climate, this is a very tricky issue that we have to think about because we can download something prepared as WorkClim or CHELSA. I don't know if you know these databases, WorkClim, current and future forecasting, CHELSA, similar, a lot of information. And of course, we have the Copernicus database from which we can download information. That information we can put in our study area, but if we make a zoom, we have a mismatch with the pixel size of the information that we have from satellites, from digital visual models. So we can here spend time also working in a regionalization. We have already climate products with a regionalization, and then we can reinterpolate using some smoothers or having everything at the pixel size. That's a GIS thing. And then we arrive to the soil properties. I told that in my PhD, we created our own soil map. So here in Cantabria, we started for the Nature 2000 areas, then we enlarged it to the whole territory. We created also our soil properties map because there was not information. And it was very important having information about the pH, about the soil texture, for the differentiation, for example, of the acidophilous beech forest and the eutrophious beech forest, and among others, of course. And the grasslands is very important, the soil information for the grasslands. So what we did here was creating somebody as a strata, different strata, 12 homogeneous areas. Then, as you can see here, we took into account, of course, the lithological units, accessibility for sampling, and make a field sampling that was afterwards moved toward the lab sampling, statistical analysis, and so on. And we end up with maps, with regression maps and with mechanistic maps, and a paper that a couple of months, some months ago, we finally published after a lot of long process of review, because it was not easy to have, but needed to create this soil property map. Once we have the equations and whatever, we create the maps for the whole territory and include that as a new predictor. And we finally arrive to remote sensing. Of course, we can download freely Landsat imagery. We have to take into account, I spent so much time trying to get the best combination of corrections for a time series of Landsat imagery, that I published a paper on that, because I spent thousands of combinations of corrections of topography, of atmosphere, and so on. So you have to take into account that information is not pure when you download. You have to correct, and once corrected, you have clouds, you have shadows. You have to take into account that we'll have to correct some kind of maximum composite values, mosaics, for having something continuous and with quality enough that allow us afterwards to do what we know that can do the remote sensing for us, is to go a little bit more beyond our eyes. So in the upper image, you can see forest. In the below image with infrared, you can separate the pinus vegetation from the broadleaf vegetation. We can move towards more, let's say, with remote sensing with larger capabilities as Sentinel, because it improves the spatial resolution, the spectral resolution, the temporal resolution of Landsat, even though you have to create mosaics. Here in Cantabria, we are not lucky. We have 4 different images for covering the whole territory. So we have 4 different scenes that sometimes change the cloud cover, even the hour of acquisition, if you combine platforms. So you have to take into account that you have to put everything in common, in agreement. But when we had to do this in Turkey, come on, we had 40 different images to put in common, terabytes of information. But it's good, because with Landsat, it's good because you have time series. We are working here with a company, a very good company, and we are working creating our own system for downloading all the time series for the north of Spain of Landsat imagery and putting on our screens for making analysis of time series. And with Sentinel, you have a larger spatial resolution, as you can see here, and improved spectral resolution, and also the temporal resolution is also larger. You have information now each 5 days. Then that information can have clouds and so on. The Landsat and Sentinel differs not only in the spectral, but also the temporal resolution. So you can select information, let's say, for the late spring and summer, for make comparisons of some of the indicators and identify if you have one type of forest or another. And of course, you have LiDAR. In Spain, we have the whole country covered by LiDAR. It's extremely useful for getting information on the vertical structure of vegetation and the understory. It depends on the density of the LiDAR information. But we can do amazing things like this. So we have here forest patch with different height, with different age, with different diameter of the individuals. And with LiDAR, we can not only map the forest, but also map different structures that will allow us for identification of the habitat types and the conservation status. Okay, if we have a forest forested area like this, and we take points or polygons or whatever, we will see that forests are related to higher values of NDVI and higher values of LiDAR. So these indicators are very useful for this, very basic, but for showing you that the statistics behind the data support our analysis. And here we can have a large amount of questions again. So about how remote sensing and these environmental predictors can help our lives when modeling. So have you ever used this before? What about the quality, maze corrections, and time series analysis? Have you ever thought, if you are not experienced users of remote sensing, that this is not straight? You cannot download the images. I refer again to the beautiful webpage and information of Richard Lucas of last week. That was beautiful and cool there, but that's not easy. You have to download, prepare, and put everything good for doing our analysis. And then combination of LiDAR, even radar, with optical imagery, with satellite imagery, typical one of medium resolution or very high resolution, is a very key factor. But what happens with the temporal dynamics? If we say, I have LiDAR, I have everything, okay, but LiDAR is one snapshot of one day, but you will have no LiDAR the next year, and you have no LiDAR for 12 years ago. So how to deal with that? That's another thing that I would like you to think, you take into account and think a little bit on that. And finally, for ending up with this more technical block, is we have to make the models. Okay, so we have the occurrence data, we have the predictors, environmental predictors, remote sensing, different resolutions, everything corrected and well designed. Hopefully, we have an operational system that does everything for us that somebody had to work before. And finally, using the modeling procedure, typical regression, Maxent, maybe some of you know Maxent, is highly famous. We can use R with the different packages, DSMO, BioMod, SDM, whatever. Or now we are working with deep learning. We are working with a company that creates software, scientific software, and we are creating our own neurons of deep learning for running analysis of habitat mapping and vegetation distribution. What occurs then? That we have spatial predictors. We have modeling outcomes that we have to transform into maps. That's not straight neither. We have to take into account a lot of ecological theory that I would like talking to you in after a while, just 5 minutes break for allowing you breath, because that's the most important issue. That's one of the points on which ecology, the ecological theory, needs to be taken into account for understanding how we can transform our spatial predictions that are probabilistic, are spatial predictors with uncertainty, with error, with, of course, part of reliability, can be transformed into maps, into something that is objective. This is a map of the beech forest. This is a map of this particular type of grassland. Okay, and here we have like a seminar specifically designed to our scripting BioMod that is cool, it's very nice, but it's not the moment for doing that. So, Bodil, do you want to stop a little bit, 5 minutes or not?
Yes, you can stop for a while your presentation because we've got 2 questions here.
Okay, perfect.
So there's another question by Tom Harrison. He's writing, thanks, but helps, referring to the previous answer. I was interested in how to overcome the practical challenges of introducing the use of technology to ecologists, more used to using paper maps and notebooks, or even just how to convince them about the value of doing this.
What I think I understand the question is, which are the benefits of introducing technology to the field workers, more or less? That was Bobtek?
Yeah, and how to convince this, let's say, traditional approach people to use modern technologies. Yeah.
So for me, the experience in Turkey was like one of the best and most beautiful experiences I've ever done in my life, in my professional life, I mean. And we arrived there with people that has nothing to do about remote sensing. They didn't know what's a satellite imager, of course. And not only that, but they didn't want to know more about that. They wanted to go to the field and check whether the pine type, whatever, or the steep area of this species dominated by this species is there or not. So the good thing is that, first, they keep a lot of time of work, because if you go to the field and you annotate the coordinates of something, and you afterwards have to go to arrive to your desktop and to try to move that into a GIS or into an Excel file, a database, you keep error, you get a stress, because sometimes you don't remember, you write it down something that maybe it's raining, you cannot write properly, you don't remember, whatever. So everything that was put into a technological basis since the beginning keeps you time, and of course increases quite a lot the amount of quality and the accuracy of the information. When I was doing my career, I was working in a very big project with people doing the Nature 2000 maps, the official Nature 2000 maps of Spain in 1994. So we went to the field with the cars. The experts, Salvador Rivas Martinez, one of the most famous botanists of the history of Spain, and others, were just talking the alliances and the vegetation associations and so on. And we were writing down, putting points on the maps. And when we went to the university again, we were like, wow, what's this? I cannot read what I've written down here. I don't know if the point is here or the point has an arrow, because in that moment I put an arrow, I don't know why. So if you do this with technology, everything is much easier. And of course, now it's quite easy to do. All the GIS platforms has the bridges for doing this, and to allow the GIS, a lighter version of the GIS software have in the tablets, even in the mobile phones. So you can just locate, you can fill even databases. And the good part of convincing the field workers is showing them that this information complements. Don't eliminate the expert criteria. Doesn't eliminate anything. Just complement and make their lives easier and make the results better. And the best thing is to have a hands-on, to work on that, to show them that it actually works.
And I've got another question. Nico Jeff Gapner asked us, how did you prepare soil properties maps? So thinking about mapping soils.
Yeah. So for the soil mapping, we started working with soil grids. Maybe you know all of you know soil grids. So we started working with soil grids, but the spatial accuracy of the information was very, 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 very light. So I mean, was not a relationship between the soil grids information and the distribution of our vegetation types. So we need to go in more detail. So as I explained, what we did first, like in the A and B part of this figure, you can see what we did was to stratify the territory in homogeneous areas. So areas that are homogeneous in terms of altitude, slope, aspect, vegetation type, land use history, soil radiation, even a realization of climatic conditions. So then, put in common with lithology, with lithology, we identified areas to be sampled for having a geographical and environmental coverage of the territory in terms of soil properties. I mean, I would like having done 100,000 soil samples, but we had no money for that. We had money for doing 120. So we had to stratify the territory for distributing that 120 samples in the most efficient way. Then we went to the field and we made some profiles in some of the points, and other points we only took a sample of the soil, of the topsoil, and then we went to the lab. We analyzed all the properties that you can read here in the table, pH. We made a contract for the person, an ecologist that was with us 6 months or 8 months working for doing the lab analysis and so on properly. So we got information for that points about all the properties that we analyzed in the lab. And then we ran regression analysis, typical stepwise regression analysis, because we had the predictors, we had the point, regression analysis. But for some properties, soil organic matter, we had to create mechanistic modeling approach because the regression map was not accurate. You can see here for the soil organic matter, the result of the regression modeling and the result of the mechanistic modeling below. So this is the result of the paper that is here. I can prepare a number of papers and send afterwards to Botec, and we can send to all of you if you want, or you can look to my ResearchGate profile and you can download from there. It's a paper on which we explain all this, sample, modeling, lab work, and so on, because it was a hard and intensive task, but we had to go to the field. In the same way that we go to the field to sample vegetation, we went to the field to sample soil properties, and then we model using digital soil mapping approaches.
Thanks a lot, Jose. And so we've got 20 minutes left, no more questions for now. So I would say 10 minutes for last part of your presentation,
okay.
and 10 minutes for the last Q&A session.
Perfect.
So I will switch on my camera in 10 minutes.
Perfect. Well, thank you very much. So finally, what do we get from these maps? So which are these spatial predictions and which are the maps that we can create from that in situ data with remote sensing? So we published a paper a couple of years ago that has a lot of relevance, and we are capitalizing our knowledge in the concepts of that paper that I will show you afterwards. But it starts from the concept of the IUCN about the distribution of biodiversity. So the extent of occurrence and mainly the area of occupancy. The area of occupancy, the IUCN defines as the grids in a grid cell environment that are occupied by a species, by an habitat, or whatever. So what we do with our analysis is basically the same. We define different levels of the area of occupancy following the IUCN criteria. You can see in the paper of Methods in Ecology and Evolution a detailed explanation of all this. But basically what we say is that when you model biodiversity, in this case vegetation or habitats, using only environmental predictors, you get potential distributions. You put the distribution of one species only with topography and climate, and you will have a potential distribution of that species. But when you include the remote sensing, satellite information, and LiDAR, what you do is like what we call in species distribution modeling, what we call the biotically niche reduction. So we put something potential into something real, something current, something local, okay? So when we model each habitat, only one habitat, by combining environmental limiting factors and remote sensing, we create what we call the local area of occupancy. It's like the real distribution of that habitat across the territory. But the real distribution of that habitat in all the conservation statuses. I mean, for example, imagine a beech forest, and we will have, in the upper part, you can see a green, dark green color and light green color. That's what I mean, more or less. So we have areas on which that beech forest will be very well preserved in a very good conservation status, and areas on which the habitat type is not in good conservation status. But anyway, the habitat is there, okay? But what occurs when we put a lot of habitats in common in the territory? What occurs is that we never have a crisp line, as we have, for example, I don't want to say that Corinne is not good, but what I say is that we have not, in reality, when we are talking about vegetation and about landscape ecotones and landscape continuum, of course we have a crisp line when we have a grassland and a forest, because sometimes the grasslands are managed and the line is sharp. But when we are talking about vegetation communities, we have not sharp lines. We have like fuzzy ecotones. So that's what occurs when we put in common different habitat types. We get what we call the realized Rf occupancy. This Rf occupancy is the areas only dominated by that particular habitat. If you see the image, the green, the blue, and the yellow color in the line of local Rf occupancy, they occupy locations that overlap. When you overlap all of them, some dominate and others dominate in other locations. So that's what occurs in reality, and that's what we can do by modeling vegetation with remote sensing, okay? This is the paper that we published first about the general concept, and we did the same for riparian forest distribution, only talking about vegetation distribution, but it's the same, more or less the same concept. And that tracks the ecological niche theory. That's one of my favorite books of Thorsten Peterson and collaborators about the ecological niches and geographical distributions that talks about the species only distributed in the abiotic environment, biotic environment, and taking into account dispersion. And that's something similar. We can model only with environmental limiting factors, potential distribution, or model something more real, more local. the first consequence of this in terms of the maps that we produce is a reduction of the area occupied, of course. The potential distribution here occupies almost the whole territory, but when we move to the local area of occupancy, the real distribution, it reduces, and when we only map the areas dominated against other habitat types, they are even smaller. We have done this exercise for the whole our region, Cantabria. We are doing for the whole north of Spain, and we did this in Turkey. So the amount of area occupied changes, and this is like a look map. This is how look like a map of one habitat. This is the dry headlands. Okay, if we go in zoom, this is the map on which we identify the area on which we have headlands in good or in bad ecological conservation status. This is one about ecological beach forest, or acidophilous beach forest. So we have the forest. We can change the raster format into vectorial, just put in thresholds, so we can get patches, as we can get by photo interpretation with high or less accuracy. Okay, but what occurs when we combine these forests, acidophilous beach forest, with all the other forests that we have in the area, oak forests and others? That we lost the green, light green areas because they are not dominated by that habitat type. If you go to the field, you will see, okay, I have here this tree, the beach, but here this community does not dominate, and here it dominates. So we can map that, especially by combining all the maps that we obtain from the procedure. If we do that for all the habitats, we can create a vegetation map quite similar to the ones that we can make with photo interpretation, or even like Korean and so on. Okay, and of course you can get the attributes of the percentage of area occupied and many other attributes that we want to the habitat that dominates, or the habitat that are with that. All that maps can be combined by creating by creating attributes to previous maps. Of course, imagine that you have a vegetation map, as some of you asked. You have a previous vegetation map of your territory. You run this kind of analysis of habitat mapping that give you the probability of each habitat type. Then you combine all together. You can afterwards get the information of these new remote sensing-based maps to the land patches that you have in your previous map, and you can compare. And you can do it for different databases. We made here for Corinne, for COC in Spain, for the forestry map of Spain, and at the end you get a pattern. This is the altitudinal zonation of the vegetation that we obtain from our models. When we gave this to the botanists, they told us, okay, this is a reliable pattern. So the pattern of our maps predicted was comparable with the pattern of our vegetation in reality. So that's good. That's what we did in Turkey as well. But what we have to do actually is to go to the field. Again, as I told you in the beginning, and validate. And we get confusion matrices for the different algorithms. This is the matrix of random forest. This is the matrix of artificial neural network, so deep learning. So some habitat types are mapped consistently with high accuracy, and others are not mapped with consistency because the capability of our predictors is not good enough. We have uncertainty, we have not spectral mixing, we are not using the most suitable remote sensing databases. So we have, as I told you, we have to change, let's say, from Landsat to Sentinel. This is a map that we did in a coastal area with Landsat. This is with Sentinel. We can see that the spatial accuracy improves the map quite a lot. And I will quickly just to show you this. When we were talking with complex landscapes, this is an area with a high abundance of wetlands. There's a Nature 2000 here in our region because of the amount of wetlands. It's the Lic Tierra del Escudo. Is not enough neither with Landsat and with Sentinel. So we made an approach going a little bit more far away with very high resolution satellite. We use Deimos 2 that has 1 meter of spatial resolution, but has less spectral resolution. And we run models. For C, I'm going to just move. You can see here models with all the possible combinations. Landsat with temporal resolution, Sentinel with temporal resolution, Deimos with temporal resolution, even including LiDAR, including also topography. And we made a validation and a spatial validation, try to see how we can differentiate the wetlands to other habitat types that we have around in different buffers. So as soon as we go more far away, it's easier to map the wetlands. But when we are with habitats quite close to the wetlands, but that are not wetlands, acid fence in concrete, the things are much more difficult. The good part is that we succeeded. Deimos was useful, but Deimos was much better, you can see here, when we put Deimos in combination with Sentinel. This was the best map that we can obtain, and which was validated in the field and highly satisfactory. We are doing just the same with grasslands now, but moving into the hyperspectral domain. We don't stop in the very high resolution imagery. We jump into the hyperspectral measurement of pastures, the dominant species, the habitat types of pastures. We also included phenology. We are taking samples through time, not only in one moment, with hyperspectral that give us a very high resolution of spectral information in different times about the dominant species, the habitat types. We are making experiments in the field that then we move to the lab. And finally, what we get is a spectral library that is published, freely accessible in the web in the institute. We have a spectral library that give us, using the spectral similarity with spectral angle mapper, give us which habitat can be differentiated from others and which habitat cannot. And not only that, but also which habitats that can be differentiated from other can be seen also in the typical satellites, the medium resolution, as Landsat and Sentinel. For allowing afterwards, starting with this, I finish, starting in a circle, in a round of improvement. So we start with medium resolution, we go to the field, take data, in situ data, we make models, validate. They are not good enough. We move into very high resolution satellite imagery. We move into the hyperspectral domain, so until reaching a level of agreement on which habitat need to be mapped with which remote sensing source for getting suitable and acceptable result. I told Botek and Clive in the beginning that I have another 2 big blocks just in case we have time or we're willing to continue talking about this. But all this was the topic of the meeting, habitat mapping, of the seminar, sorry. But then we have to move this into a state of conservation. So we need to assess how that patterns change through time. We need to assess which are the processes changing that patterns through time. All that patterns and processes change the ecosystem services. So I am teaching one master in the University of Origin in León. The subject I am teaching is the ecosystem service. I spend 80% of the subject talking about the modeling habitats and modeling functions, because that's 80% of what we need for modeling ecosystem services. And finally, with that information, we can create a very clever management of the territory. We can design. We have ended up with, a couple of hours ago, a congress of a project. It's called the ALICE project, that is focused on the design of blue and green infrastructure networks. So we can take very clever decisions with, if this information is done in a suitable way. So these 2 blocks, maybe in the future, I can tell you, I would be delighted. But that's another step that moves a little bit more habitat mapping. Is monitoring the state in time and applying the information for making a clever monitoring, reporting, and management of of our territory. So,
thanks a lot, Jose. Great work, great presentation. I see no more question in Q&A window for now. So, Clive, would you like to start our short final discussion? We've got 5 minutes left.
Well, I guess the first thing to do is to check whether anybody does have any more questions that they can put to Jose Manuel. It is a fascinating, sort of a really interesting piece of work, and as Jose Manuel said, he could have talked a lot more about it, I think, and there's a case for maybe another webinar later in the year, sort of building on this one.
Yeah, thank you.
I could understand Tom Harrison's question to some degree about the how easy it was to introduce the concept of sort of introducing technology to traditional ecologists in the field. it's an issue that's it's not just the UK. When I know that they've had similar problems with this in the Netherlands, you know, it is a human thing. I think is that humans can be quite resistant to change.
Yeah. So I just mentioned one issue that when we finished the first day the round of modeling, and I traveled to Ankara with the final maps in my laptop, because we just finishing the maps with no validation at all. So I arrived to Ankara, and the day after, we had a field trip with 40 people in a bus to look for 4 or 5 spots that they had selected without telling anything to us. And they wanted to see that places were not sampled, and they wanted to see whether the maps were able to predict the occurrence of shrubland type, a couple of pinus patches, and some steep areas and so on. And we had no idea about the place. We had no idea about nothing. So the good point, we were lucky because we more or less were accurate. But the good thing is that they understood the procedure. So now is famous now the Living Lab approach for engaging stakeholders with remote sensing. We made like the first attempt of a Living Lab, because we engaged with them, explaining since the beginning that I had the final slide that I couldn't show you because it was at the end of that 2 blocks. It's a big sentence of remote sensing does not replace anything. It complements our capabilities. So they understood that. So always the point, the in situ data was there. But remote sensing enlarged it to the whole Central Anatolia or to the whole north of Spain or Europe. Of course, there are places, Netherlands, for example, or Germany, that has a very, very detailed information about some areas. They almost know everything. I mean, in that case, maybe it's not interesting for mapping remote sensing. But what about monitoring? So if you can track from the past to now and for the future, that's a good point, the monitoring. No?
Yeah, my own experience with this is that it's sort of like a step-by-step process that you start off finding out the things that you can do easily by simply going out and, like you say, checking, ground truthing, so to speak, and then finding out what you can't do, and then you have to go back and say, well, okay, how can we collect more information? But your focus shift is from the things. Now you know you can do these things. You don't have to worry about those. So now you can focus on these ones. And so it gets, you know, you focus in more and more until you reach the point, well, maybe we can't do that using remote sensing anymore. But there's already a big base of information behind you that can be collected automatically then. And, you know,
yep.
So it is an iterative process, but my experience, okay, so we know we're never going to be tracking sort of annual plants and things like that using remote sensing, but we can track the opportunity for annual plants using remote sensing by tracking the changes in open ground. So it is maybe just changing the way ecologists think, you know, evolving to accommodate this incredible technology that's available to us now that wasn't maybe 10 or even 15 years ago. And if you throw drones into the mix also.
Yeah, I had some slides about drones, about many things, and a good point that I had no time. It was not within the topic of habitat mapping itself. But we have a couple. I can hear Carlos Arroyo, for example, and Ivan Pastrana. They are the attendees. The list of attendees are master students that made that are working or they did the master thesis here, and everything is based on the time series. So of course, the mapping capabilities of 1 image or 2 or 3 images for creating a pattern. That's for us. I don't want to say that it's like the first step, but it is. But the good point is that we afterwards now we have make here of our own system. We are working with the open data cube approach as well in the institute, but we created with C++ our own routine for downloading for our region the whole time series of Landsat imagery, of Sentinel imagery, and of MODIS for the whole territory. That all the images since the beginning, Middle 80s, and all the Sentinel and all the MODIS. So we have a routine for creating time series for working with spectrophenological analysis, with spectrophenology. So we are now focusing on understanding the trajectory, the trends from past to now and in the future of each pixel that was mapped already into an habitat type. So with that, we can assess the structure of forest, we can assess or we can forecast some scenarios of future dynamics of grasslands in the base of they have been managed or not. So that's the good point of using the capability of remote sensing for monitoring and for tracking in the future forecasting. Once you have the patterns,
Wonderful. Thanks a lot. Thanks a lot, Jose. Running out of time, I've got just a final message from Tijana Nikolic, our other member from Serbia. Thank you for this great talk, Jose. I think that all we would like to say also. And before you go, I would like to share the last slide with information about our last meeting, last webinar in this series that we'll have in 2 weeks. Same time at 2 p.m. Central European time on Wednesday. So in 2 weeks we are meeting again, and Sander and Stefan from Wageningen University will speak about European Unis habitat suitability, probability modeling and mapping, and the European Vegetation Archive. So feel invited to the last webinar in this series, and I think that we'll have soon another series, but maybe in autumn. But I hope to see you all again in 2 weeks. Thanks a lot, Jose. Thanks a lot, Clive, our chair of our group, and I would say thanks a lot to all our group for the cooperation in this great webinar series.
Thank you very much.
Thanks. Right. Thanks again, Jose Manuel.
Thank you.